occurs. So there's some limited degree of control that is able to be there, but it isn't really control. It's mostly just doing a faster or a slower type of evaporation that can be done.
Okay, thanks. We have a second question. The question is, what advantages does the system have, in particular to solid-state problems like polymorphism and amorphous instability?
Well, I think there's a number of advantages. One of the big advantages is that we can handle, we can really explore a wide range of different crystallization processes and generate things with a very small amount of material. We can then really analyze the solid state, and we generate it in a format in a way that allows one to analyze things with a variety of different types of analysis. So you end up with a set of samples that you can take that set of samples. You can analyze it with microscopy. You can analyze it with Raman. You can analyze it with X-rays. You get a full characterization on that. All those are non-destructive types of tests. So one can even take those. You can then expose you can even store that set of samples for a period of time. You can store it at room temperature. You can do thermal cycling of that. And you can look for changes that may happen over time. So you can look at the stability, look at whether your form migrates to a more stable form or a different form based on the conditions that it's stored in. So I think it's a very convenient way and a very efficient way to achieve things. The last thing is that it allows for a great deal of consistency in terms of being able to generate and if you're going to do 400 different crystallizations, you'd like a way to be able to compare these to each other. All these are done on the same days in the same stock solutions. They see the same thermal history. Makes it very consistent in order as a way of comparing different types of crystallization processes.
Okay, we have one other here. How much quantity is typically required for the birefringence analysis?
So birefringence analysis, this is a very good question. So you can see here on the slide, I think I talk about here using between 0.5 and 2 grams for the entire study. You can imagine that if we use a ½ gram for the full study, and then ½ gram gets spread over 4 different plates, what we end up with is about, on average, about 1¼ milligrams per sample. So you have, picture you've got 96 samples per plate, 384 wells, so it's about 1¼ milligrams if everything was uniformly distributed. The big reason for doing that is that in order to get X-ray analysis, that's really what would drive needing. That's the type of analysis that needs the most amount of material. If you want to do X-ray analysis, you need enough material there in order to get a decent diffraction pattern off of it. For very early screening, it's very possible to do things with much less material, and you can do things with just Raman or just Raman and birefringence. In which case, you could actually do a fair bit of screening with something less than 100 milligrams of material and do a pretty broad screen. If you start getting much less than that, you would have to really look at how broad one wants to screen, how many different conditions, and then you're really trying to decide how early on you're trying to screen. Very early on, you may be not interested in doing all the different processes we talked about here and really focusing either on evaporation, sort of slurry experiment as well. I should say that the workflow that I talk about here, both in terms of software, hardware equipment, is fully able to support those very early studies where you have we call a sparse matrix, where you have very small amounts of starting material, and doing a much narrower study very earlier on, or a study much later on where you've got a very broad, you have more material available and you can do a more full and more broad study.
Okay, following up from that, we have a question then. How about the consistency in scaling up the reaction from the microgram to the gram and then to the kilo?
Well, so I would say that we do, the scale up, we generally do pretty well in terms of scaling up to the many milligrams. So I talked about in the case when we do scale ups for verification, our scale ups in this particular context are still quite small. I mean, we're still talking about going from a 1 to 2 milligram scale to a 25 to 50 milligram scale. That's still a very small amount of material. And the scale-ups in this context are really intended to verify the form and reproduce it and get enough to do destructive types of testing. With those, we do a very good job. It is fair to say that some of the processes that are outlined here are easier to scale than others. Things like cooling and in particular are sensitive to the heat transfer that is more difficult to scale. But I mean, the scientists we have in the lab actually have done pretty well with knowing how to scale that and what types of things to do to get scalability. Going beyond that, going to much larger scale, kiloscales, other types of things, we've done pretty good work in being able to transfer methods back with our clients. And I think our customers, whether it's at Merck or Lilly, other companies, have talked about the ability of being able to transfer methods and find methods that have allowed them to be transferred to manufacturing processes as well.
Okay, we have quite a few questions coming in. Another one here is, how will the instrument go about if I wish to carry out solid-state stability study? And can it provide humidity along with temperature condition control?
Sure. So the answer is we certainly can. This whole process could be used for doing solid-state stability studies. The robot deck itself does not provide a unique humidity environment. Although I don't think you necessarily want one. Typically, if you're going to store things at different humidities, there's no reason to necessarily tie up the robotic deck. You would typically want to store things for typically a day or several days, or up to a week at different temperatures or different humidity conditions. In which case, you really want to have your robotic deck free for doing other types of studies, preparing other samples, doing other crystallizations, doing analytical workup. So the way we do those in our lab is we prepare the studies like I talked about. Samples are generated. Then those samples then are stored in a various types of humidity chambers that are set at different types of humidities for different lengths of time. You can log them into the software, so you can log them in and bring them out. You can record exactly how long samples have been staying at each of the different environmental conditions. And then when you go back to the X-ray, we would end up having a series of either X-ray analysis or Raman analysis. And so you can look at how the X-ray analysis changes over time, and they'll track that as a function of time, as a function of either humidity or temperature as well. So really, in this particular case, it's the integrated informatics and the software that really provides the power of being able to do these types of things, and a format that allows you to do this type of analysis in a non-destructive way, be able to do the analysis over and over again using the same set of samples.
Okay, I think we'll take one last question here. The participant sees the strength of the system in terms of being able to scan different variables for looking for new polymorphs. What if their problem is actually trying to hone down on a known polymorph and reproduce that? Do we have experience in that?
Yeah, we've actually done a fair number of things. We've done things with looking for known polymorphic forms, trying to really understand that and trying to understand, in some cases we've done that trying to find either a more efficient process or a more convenient process or a more cost-effective process to generate a particular polymorphic form. In some cases, just from a process development standpoint, one is interested in finding something of a more optimal crystallization conditions or looking at the crystal habit. So one of the items you get, and I'm not sure that my pictures show it well. I'm not sure these really do. It doesn't come through in PowerPoint, but the images you get here from the birefringence are actually quite good resolution, and you can tell the difference whether you have very long, thin needles, whether you've got more cubic types of crystals, whether you've got a really fine set of fine particles. And so, in some cases, we actually look for conditions that give a crystal size and shape that is more convenient and something that would be more optimal for processing conditions. And again, so you're looking within the same polymorphic form and either trying to find the conditions that would either generate that form or generate that form more efficiently, if that answers the question.